Next, let's move to question 12. So this question asks us to determine the pH of 0.15 mole of ammonia. Next 3, with the constant, the constant is 1.8 10 power 55. We know that ammonia. First, as a chemist, we need to know the common type of chemical that is categorized in acid or base. So now the ammonia, we don't know that ammonia is we categorize it in a base. So for the base, for this one, for the ammonia reaction, once this ammonia we dissolve it in water, so we will produce ammonium ion and hydroxide ion. So OH mean that this one is a base. So again, I already like to use this table because it's easier for me to see the change of composition of each species in a system. So in our system we have ammonia, we have ammonium ion, and so we have hydroxide. So NH3 we have NH4 plus and NH minus. So at initial we have 0.15 ammonia and we have 0 for ammonia and 0 for hydroxide ion respectively. So the change is depend on the coefficient of each species in chemical equation. So we have minus X because once we dissolve it, of course this one will be reduced and this one will be increased. So that's the change with minus S plus N and plus S, and the group constant is 0.15 minus S plus N and plus S. So again Kb. So for the constant is product of reactant. So product here is ammonia ion and also hydroxide ion over ammonia and then we know that this one is SS and over reactant is 0.15 minus S at equilibrium. So again we use this relationship 0.15 minus S. S is too small, so we are using 0.15. And again if you like to use this kind of postulate or assumption, you still can calculate it one, but however the question or the work will be a longer, and again if it is involved with the power of 3 or power of 4, it will be more complicated. To make life easier, we use this relationship, and this so it will give not very much deviation from our actual answer, and then our S square will be to have a 2.7 10 power 6, and if we rearrange it and this one is our equation, we can solve it and we get the S value is 1.64 10 power 53 or negative 1.64 10 power 53. Because this one is concentration, we can ignore this one because the concentration can't be negative, so we just can ignore this one. And again POH, POH equal to negative log OH, because now we know that the POH of our equation is depend on the concentration of OH minus or the hydroxide ion in our solution. So we have plus X, so negative log S here is 1.64 times 153, so we have 2.79. Now we need to know that this one is base, so pH of base equal to 14 minus this, and it is POH. So we need to remember this relationship. Write it again in a proper way. pH for base equal to 14 14 minus P OH. So here is, so that's why we have 14 minus 2.79, that's why we have 11.21. So the pH for our B solution is 11.21. Again, calculate the dissociation constant for question 13. We move to question 13. Calculate the dissociation constant of conjugate base of HF or acid given the Ka equal to 6.8 times the power of negative 4. So we know that HF equal to H plus F minus. So now the question asks us the constant of conjugate base. So we know here is the other relationship. When we dealing with acid base relationship, we need to remember this relationship. So Kw equal to Ka times Kb, where Kw is 1.0 times 10 power negative 14. So if, remember that if we put in explosion factor, so we'll get this is 14, because total of pH is the value of pH is total value of pH is 14. So we have 1.0 times 14. So by using this relationship, Kw equal to Ka Kb. So Kw is 1.0 times 10 power negative 14. And the question already give us the value of Ka. So we just plug in our question and we get Kb equal to 1.47 times power of negative 11. Then we move to the next question. So question 14, question asks us to calculate the concentration of H3 plus H3O plus ion, or H. This one is hydrogen ion, or you can call it H ion, or in a mixture of 0.02 molar acetic acid and 0.1 molar sodium acetate, given Ka for acetic acid is 1.8 times power negative 5. So now, this is quite a bit tricky because the acetic acid and sodium acetate. So acetic acid is a weak acid, so which is ionized partially, while the sodium acetate is a strong electrolyte, strong base, which is ionized completely in the solution. So now we will have a two equation. So we have H3COH, which is this is what is acetic acid, H2O. So we'll have H3COO minus plus H3O plus, and so this one is dissociation of sodium acetate, which is a strong base. So we'll have H3COO minus plus Na. So here is we have two ions. So this one is a common ion effect. So this was common ion because common ion. So you can see it. I explained about the common ion effect in my lecture. Okay, for this one, how to calculate this one? So first thing first, we need to remember this relationship where acetic acid and sodium acetate. This one is acetic acid, and this one sodium acid is a weak. The acetic acid is a weak acid, while the sodium acid is a strong base. But if it's meant by weak acid, what is meant by strong base? So weak acid means that it's ionized partially, while for the sodium acetate is a strong base where it's completely ionized, deionized in our system or in our solution. Okay, first what we need to do is we know that for initial concentration, for we take H3COOH first, and if we dissociate H plus and H3COO minus. So for the concentration, you have 0.02, 0.01, while at the concentration you have why here we have 0.1 because this one is came through this one. This one is the acetic acid, which is a strong base. Because at the initial it have 0.1 because this one is a strong base. 0.1, it will dilute, it will deionize completely. So that's why we have 0.1 molar of aqueous of acetic ion and 0.1 molar of sodium ion. That's why we have 0.1. To change, we have it will be reduced minus S. So your H plus will be increased plus S and plus S, and at equilibrium we have 0.02 minus S. plus S and 0.1 plus S. So here is the relationship that we need to know. This is about the common ion. And then again, Ka equal to product of reactant. Now our product here, the concentration of H plus and also acetate ion over the reactor. Reactor here is the acetic acid. So we have the Ka here. The Ka of acetic acid here is 1.8 times 10 power negative 5. Put here, substitute all the value in our equation. So Ka equal to 1.8 times power negative 5 x H, the concentration of H plus is x, and the concentration of acetate ion is 0.1 plus x over 0.02 minus x. So what we can do is here is plus with plus. So here is our relation. 0.1 plus x. So we can consider this x. The value of x is too small, so we can ignore. So that's why we just take 0.1, and for the other one is 0.02 minus s. We can ignore that the value of s is very small. That's why we just take the value of 0.02. So we rearrange everything here. So we will get s 1.8 times 10 power negative 5 times with the concentration of acetic acid over acetate ion, like this. We just move to our left hand side. So we have s. We have when we compute it, we get s equal to H plus, or concentration of H plus. Concentration of hydrogen ion will be negative 3.6 10 power of negative 6. So the question asks about to calculate the concentration of Hg plus ion, so we already calculate this one. So Hg plus is Hg plus here, plus and H plus is the same thing, or same species. So here is how we calculate the question that involved with the common ion. So here is the common ion effect. So that is the way where the common ion effect taking place, where it will the common ion will be affect, or it will contribute to our solution. That's why we will know this relation, this kind of relationship. So it will make our answer better, and we can calculate better in terms of how to answer this kind of question. And if we encounter this kind of problem, we know what to do.